Hello friends of plasma-based wakefield accelerators. Welcome to my channel. So I'm back with a new video, but this time this video is a request from one of my viewers and probably subscribers. I was asked if I can simulate the generation of shocks in a supersonic flow. In this specific case, the shocks are generated by a blade. So this type of density profiles, so what they are called fast down ramp, are used in plasma-based wakefield accelerators as a method of electron injection. It can create very good quality electron beams and debatable also quasi-stable. So let's start. To keep things easy to follow and simple, we will use the very first simulation, the very first case that we did in this channel, so 2D axisymmetric, which we will modify accordingly to generate the geometry. We could use this case, so 3D conical, but it's better to start with this one just in case some of you watching this video are new and they haven't followed the rest of the tutorials. So I will have 2D axisymmetric. So what I do, just right click on it and I just duplicate it. So it will copy everything that is here, so that is the duplicate, and I will modify after that. Drag it somewhere here, just for convenience, give it a meaningful name. All right. Okay, so now this is the 2D axisymmetric geometry. Okay, XY plane, right click, look at, just to see it better. Make sure the units are millimeter, because the geometry is in millimeters. It's easier to draw and see the entire geometry. Now for this case, we will not need any surfaces here, so we can just delete it, and we will have only this sketch. All right, and now this is a 2D axisymmetric geometry, and we use it to generate the 3D geometry. So that is done easily. So create, revolve. The geometry is the sketch, and axis, depending what you choose. So this axis, you see, is pointing in the direction in which you want to revolve. Of course, this is the wrong one. Like this, yes, is the wrong one. So it should be something like this. Apply. So here you have the direction, and if you have full revolution, 360, or if you want just partial generation of a geometry, you can choose from here the angle. So this is the nozzle, the conical nozzle. You see it here. This is actually the nozzle. This is just a region outside where we want to check or we want to monitor the density profile. So the laser is focused on somewhere above this this nozzle. So here is the outlet of the nozzle. What you can do here, just select multiple surfaces. So this one, and this one. So if you want to select multiple surfaces, just keep Control on the keyboard pressed like this, and now right click on it and call it name selection. So we just define the boundaries. You can do it now or you can do it in the meshing program, but it's let's do it now, and let's call it pressure outlet. So it's 3 faces, 1, 2, and on the back 3. Generate. Nice. Okay, now let's define this as an inlet like this. Right click, name selection, apply, and let's call it pressure inlet. All right, generate. And now let's just hide pressure outlet. So hide face. Let's keep for now just this geometry. You will see why in a bit. So this is the nozzle inside, all is good. And now let's create the blade. In this case, just to keep it simple, I will not create the geometry of a real blade. So a real blade, you know, it has it's a plate and it has a very sharp edge. Now I will not draw the very sharp edge. It will take too much time, and it's really beyond the scope of this tutorial. You can do it when you will do your own simulation, because it depends on what kind of blade, you know, if it's very fine, if it's rough, if it's I don't know, whatever you want to use. So that is easy to draw if you and simulate if you know this this tutorial, or you know the steps in this tutorial. All right, so and to generate the blade, or let's call it plate, maybe it's better. Create primitives and box. And for now, let's give it just a few dimensions, very small. So you see here, you can even press generate. You can always change it, so don't worry about this one. So you see it here. All right. Now one thing before anything else, instead of add material, so add material, if you have this checked, when you add any body or surfaces, it will be integrated in the bigger geometry. So it will be like unite two geometries, and whatever intersects is common and disappears. So only what it doesn't intersect is kept. So that's why you see here this thing. So choose frozen and generate. All right. Okay, and let's now do something. So we will need now the distance from here, from the base of the nozzle to the outlet. So to check that one, we will use analysis and distance finder, and we will choose edge, check this edge, and check this edge. And we are interested in X direction. So this is 3-dimensional, so you will have 3 dimensions in X, Y, and Z. So in Y is 0, and in yes, so it's 0 in the other direction. So X is 7196. So write it down, this one, because it will be important in the next step. All right, so box, and now let's translate this box to the outlet of the nozzle, 196. All right, we can press generate. We moved the box, and now let's make it look like a plate. So first we will make it thinner in the X direction. So let's say 100 microns thickness, so 0.1. Okay, so you see like this, and now let's make it longer in this direction, so it will be as big as the nozzle, so Y direction, so it should be here. Let's make it 2, and now you see here it's exactly in the middle, so we need to translate it. So all we have to do is in the Y direction here, -1, and generate. All right, so pretty much the blade is done. So it's exactly in the middle of the nozzle. So if you need to translate this blade like this, you can do it. If the blade is bigger, so that always covers this part of the nozzle, you can change it from here. So you can do this in any time. All right, now let's do something else. Now so if you keep like this, so if you have two bodies, this one, so the nozzle, and this one as another body, you can do that. But when you go to the next step and you start to mesh it, the meshing program will see this body as an independent body, and it will take into account the interior of it. So it will try to measure the interior, and if this body is extremely small, you'll need a very small mesh, and it will be more and more difficult to mesh it. So to avoid any problems, since anyway we don't care about the properties, I mean the thermal properties of this body, there is no heat transfer between the gas and this plate. So it's considered adiabatic like the rest of the wall, so the nozzle wall. So what we will do, we will create an empty plate. So that will be it's just a thin wall basically around nothing, around vacuum. So to do that, we will subtract from the big geometry this body or this plate. So to do that, it's very easy. So you just go to Boolean and subtract, and target body is this one, and tool body is the plate, and generate, and boom, we have just one body. So one body is the big nozzle, and inside the plate with nothing inside. Okay, pretty much we are done. So all we have to do is just to help us, you'll see now why. So just click on surface here, click on this surface, right click and hide, and now go here and select box select, click on this one so that you can select all the surfaces, because otherwise you need to zoom and select this one, and select, so it's taking time. So it's just to save time. Name selection and wall plate. We just give it a name. All right, there are 6 faces. Always check to make sure that you selected properly. Generate, and this one is pretty much done. The geometry is pretty much done. Show all faces, everything is fine. So you can see it here. So we finished with this step. We created the geometry, and we go to next step, which is meshing. Now for meshing, let's not keep the previous information. It's better to start fresh. So just press reset, and also to the next step to ANSYS Fluent or the setup. So reset. All right. Now let's go to mesh. Okay, let's wait to import the geometry. All right, now the only mesh that you can use here, so right click, insert method. The geometry is just click on the screen, it will select everything because it's only one geometry there, one body. And instead of automatic method, choose Cartesian, is the only structured mesh that you can use. So you have multi-zone and Cartesian, so only these two can be used. So multi-zone cannot use with this geometry, at least as it is. You can use it if you start to split the geometry in simple bodies and after that mesh it, but it's too much headache. So I prefer to use Cartesian. It's the result is good. Now we go to mesh sizing, quality, smoothing, high, mesh metric to show us the quality is just a statistic, so it will not change anything here. And at meshing, let's put 0.00005, let's say. This will give us about 1 million cells, 1 million something cells. If you are using ANSYS Student, don't go beyond 1 million cells. That's the limitation of the software. Otherwise, you cannot run the simulation. So when you try to import in ANSYS Fluent, you will get a warning and the program will exit. So in my case, I don't have any limitations. So I chose here 5, right click and update. And I wait for a little bit to mesh it. It will take 1 minute. If you want to see the status of the meshing, just click here and you can see here what is happening. Now keep in mind, each time you will do this kind of simulations with shocks, you will need an extremely fine mesh, because shocks by definition are extremely small regions in space with high density. And to resolve them properly, you need to make sure that you have a very, very fine mesh. Otherwise, the result will not be accurate. So be careful about that one. Always run, how they are called, mesh independence studies. So you increase the mesh until you increase the number of cells in the mesh until the solution doesn't change anymore. So you have to be careful about this one. So you monitor the shocks, you monitor whatever is required to monitor, and make sure that it doesn't depend on the mesh size. All right. Okay, so we have 1 million and something cells. Let's check. Pressure outlet is this one. So always it points towards the boundaries that we named. This one is fine. Pressure inlet is inside, so that's is here. Pressure inlet, and wall plate is inside. You cannot really see it. Let's assume everything is fine. I'm happy with the mesh. Actually, I'm not quite happy in this case. I would prefer to have 2 or 3 million cells, but to keep the video short, I will just carry on with the rest of the tutorial. Okay, you can close this one. We finished here everything. We close the program and we wait forever to close it. So when you close the program, it automatically says whatever you have done here. So probably that's why it's taking so long. Okay. Now if everything is fine, you have here a check sign. Let's go to setup and double precision. Here the number of parallel processes 4 if you are using ANSYS student, unlimited by the license, I mean limited by the license otherwise. So the next is 128 if I remember well, a license, and then it goes in steps of, I think the next one is 5 multiplied by 128, so they are packages. Nevertheless, it doesn't matter. All right, we choose double precision, we choose the number of parallel processes, start. Okay, nice. Scale, we draw it in millimeters just to visualize. It's better to have this one. Also, it's good to write down these values because it will help you when you will take line outs to extract the density profile. So you'll need the limits of your domain. So basically, this one is between -3 and 3, -3 and 3, and from 0 up to 21.196. Close, press check. This will check the geometry to make sure that everything is fine. It will give you statistics about the volume, blah blah blah. If everything is fine, you will not get any warning. Report quality, if you know the meaning of quality, you will have here all the details. And units, here I like to change the units from density in kilograms per cubic meter in atoms per cubic centimeter. And for helium the factor is 1 over 15.045 only for helium. If you want to calculate it, you just use the ideal gas law, transform from pressure to density. So it's fairly easy. All right, and we take this factor, we put it here and here, multiplied by 10 to 19 atoms per cubic centimeter. I like to use this one. Feel free to use whatever units you want, excepting imperial, which suck completely. Okay, density based. The solver is density based. Always use density based. We will use a steady case, not transient. Maybe sometime in the future I will do some of these cases, but for all intents and purposes, steady is good enough for what we need in our field. Let's go to model. Energy, always energy equation. Okay, that's all we check here. By default, it is taking the proper model. Some people, they prefer for this model, the K epsilon. I prefer K omega. If you like K epsilon, feel free to use it. I always used K omega, and it's good enough. Okay, we don't have to do anything here. Now materials, we need to import the material. Double click on fluid. Sorry, on materials, and create edit. Now we will import the gas that we will use in the simulation, and in plasma-based wakefield acceleration we are using hydrogen and helium most of the time. So I will just import helium and copy, close. All right, press change, create, close, and now double click. Sorry, so we have fluid. Double click here on helium, and instead of constant we will choose as an ideal gas. Change, create, close, and we go cell zone conditions. Double click on fluid, and instead of air, which is by default, we will use helium. Don't forget to change this, otherwise the simulation will be run with air. Apply, close, and now double click on cell zone conditions. Operating conditions 0. That means the gas target is surrounded by vacuum, so that will be your reference. Okay, boundary conditions, pressure inlet. The units are in Pascal, so that means so I want to use like 30 bar. 30 bar, that means 3 million Pascal. Here we will put a value that is so supersonic initial pressure, just a smaller value than the total pressure. This is used just to initiate the flow, so don't worry about this value, just slightly less than this value. Hydraulic diameter, I prefer to use this specification method. Check, if you press help, you will see in the documentation the definition of this one and how to choose, or use Wikipedia or fluid dynamics books and so on. All right, apply, close. Now we have the outlet. The outlet, initially let's put vacuum pressure. If it doesn't work, then check in the video about the divergence of the solution, how to correct this, how to solve the problem if you have a divergent solution. Here again, hydraulic diameter 5%, and doesn't really matter here what you choose, it doesn't affect the solution. Close, and we check here to make sure we have proper walls. So if you right click wall plate and display, you'll see only this one, and if you right click on the rest of the wall, display, you'll see here the nozzle. You don't see this part because this is the outlet, so this is the entire wall. All right, we define the boundaries. Now at methods, second order upwind, we don't change anything here. I forgot something, no. Okay, yeah, so at methods, second order upwind, this is a very accurate solution, we don't change anything. At controls, we don't change anything unless the solution is unstable, so we need to reduce the current number. Then but check again my video on how to control the divergence of the solver. Okay, we don't change anything here. We go to monitors, residual. I like to have here 10 to minus 5 residuals, even if your simulation doesn't reach 10 to minus 5, but I prefer to have the residuals as low as possible. By default is 10 to minus 3. You can keep it 10 to minus 3. It's not really that critical. I prefer to do it like this because it's okay, but it's just one of the criterion to get a good convergence. So don't be worried so much about this about the residuals. Okay, report plots. Now you can do it also report files if you want to record. I don't really care at this step. I just want to see a plot of the evolution of the density at the outlet. So I create a report plot. Okay, so new. You don't have to click on this one. I just clicked by mistake. Okay, surface report. It doesn't matter. You can use facet maximum. All that matters is to monitor it. Pressure outlet. Okay. Now click on this one. Add it. Okay, you can delete one of these. Okay, and close. So that was duplicate, that's why I deleted one of those. All right, now initialize. So it's complaining that the convergence tolerance was not reached. So usually this happens if the mesh is not fine enough. The simulation will be okay. So if you are careful to control it, it will be fine. But sometimes it's not fine. So this warning will have a serious meaning. So no matter what you will do, the solution will diverge. Yeah, it will diverge. So if that is the case, just increase the number of cells in the mesh. That's why I told you that instead of 1 million cells, I prefer to have 2-3 million. So it's just experience. All right, calculation activities. Autosave if you want. It's a good idea to autosave. And from edit, keep as many files as you want. You can retain all of them or just the last 5. All right. Run calculation. Check case. If you forgot something, usually the program tells you. If you did a mistake, it tells you no recommendation. Choose number of iterations. Just a big number. You can stop it anytime, save it anytime. You can go back to whatever you saved at any time. So don't worry about this. And yeah, so let's do something since we are here. So we have seen that. So if you right click on wall plate and display, so we see the plate is in Y plane. So it's like this, and usually the laser, so the shocks are generated here in this plane. So the Z plane, we should take lineouts. So let's do it now. Plots, setup, and new surface. Sorry, I clicked the wrong thing. Line, and let's call it X1 because it's X1, it's above the nozzle. And so this is Z plane, so from -3. That's why I told you to write the limits of your domain. It will help you. And this one is through 0, and this one is just the height. So if you remember, you wrote down the distance between the base of the nozzle and the outlet. So that you will need it now. So it will be 17,196 plus 1, so it will be 18.196 and 18.196. Now here is a thing, here is a tip, and it's good to remember it. So in wakefield acceleration, actually, the nozzle is used slightly tilted. So when you use with the blade, it's slightly tilted. So the laser will see a density, different density profile than it would see if the nozzle was straight. So in that case, you need to extract the density profile at the proper angle. So if you calculate the path of that line out, you can choose here. So for instance, this one will be 18,196 and the next one, this one will be different. So you'll take the line out in angle. So from here you will do that. All right. And we give it a name here, create. And let's do another one, 9 and 9. And let's call it X2. Now for this type of gas targets, you will always work very, very close to the exit of the, more exactly, very close to the blade, because there the shocks are the strongest. So definitely you will not work 2 or 3 millimeters above the nozzle. It's not a common thing to do. All right. Now let's plot it. So when we initialized, we calculated a very rough values of the solution, and that will be refined, are used as the initial solutions and refined during the simulation. But let's plot it anyway to see how it's looking like. So X1 and X2. Yeah, so we need to activate the proper, okay. So it will look something like this. Yep. So this is the density profile. It looks symmetric, but definitely it will not be symmetric when we will generate the shocks. So right now is just the initial solution, which is very, very rough. And if you are happy with all of this, just save project. It's good to save periodically just in case something happens. And let's run the simulation for a while and see what happens with the solution and how it's going. So as you can see, the residuals are not converging nicely. Probably it's not a problem, they will go down at some point, but for a while they will keep oscillating. Is expected because not only that we have a supersonic flow, but also we generate shocks, so that can affect the convergence. But seems to be going okay. So yeah, don't forget about criteria for convergence. So all these three criteria should be met at the same time. At least this is what I use. This is how I define the convergence or converged solution. I use this. Maybe other people, they know more and they use extra conditions, but this is what I use. And you leave the simulation until it's converged, and then you can extract the data. Let's plot now to see what how is looking like so far. So if we plot, so you already see that we start to have a very pronounced, difference in the profile. So it's not symmetric anymore. You already start to have, you see here, so what is called fast down ramp. So this is the beginning. So if you're going from left to the right, so the blade is like you are seeing here, and here is a longer profile, a longer ramp, and after that is very fast down. So this helps the electron injection. So if you leave the simulation long enough, this will be sharper and sharper, as you can see here. So these are points, so these are cells. That's why I don't like to use such a small number of cells. You are missing features here because you don't have enough points. So be careful about this one. Use as many cells as you can. Yeah, I don't think I have anything else to add here. Thank you for watching. Please subscribe, and if you have the means, please support the future video releases. How to do this you can find in the video description. Thank you, and see you next time.